Okay, let's get started with this second segment so that we have a chance of finishing it. And again, I'm trying to give you kind of an introduction to the methods that are used. And this one is related in the sense that order relations are still important, but it models the components of the program quite differently. It models each reactor as a function that maps the entire input value over all time into an entire output value over all time. Okay. So we're going to still model it as a function, but the domain and the codomain of the function are going to be completely different. They're going to be the whole history of the behavior. So in particular, we're going to define a signal, which is a mapping from a tag set. It's a partial function from tag sets to values, all right? And by a partial function, what we mean is that the function is defined at tags where there is a value and is undefined at tags where there is no value. So absent is represented by an undefined function. Okay, so the tag set can be quite rich, and to be fully general, in order to support superdense time, we even allow time to be a continuum. That doesn't hurt the semantics. In practice, in lingua franca, the time values are counting off time in nanoseconds discretely, so they're not really a continuum. Okay, but you can generalize to a continuum and it doesn't hurt the semantics, okay? So in superdense time is, of course, an ordered set, and it uses what's called a lexicographic order, which is also called a dictionary order, which simply means that if you compare two tags, so if I have a time value and a microstep, okay, then this is less than another time value and microstep if either T1 is less than T2 or T1 equals T2 and M1 is less than M2. Okay, this is called a dictionary order or a lexicographic order because it's the same thing you do in a dictionary, right? You look at the first letter, and if those are ordered, then the two are ordered, right? But if those two are identical, you look at the second letter, then you use that for ordering. So the tag set is ordered with a lexicographic order. And for a particular signal, we'll use this notation to be the set of tags on which the signal is defined, which means the set of tags where it's present. Okay. So for example, if I have a clock driving a reaction producing an output, this is going to be a signal, and it's going to be absent most of the time. So the signal is modeled as a function where for most tags, this is not defined. Okay, it's only defined on the tags that correspond to the ticks of the clock. That makes sense? Got that in your heads, I hope? Okay. We use this symbol, this script G of S, to represent the tag value pairs where the signal is defined. So it gives us a simple way to represent an entire signal as a set of tag value pairs. Okay? And we use this notation to represent the set of all possible signals. I'll come back to these other definitions in a second, but let's just show how this works for reactors. So suppose that I have a reactor with 3 inputs and 2 outputs. Then I'm going to model that as a function like this. It's a function capital F that takes a tuple of signals. This is the entire trace of the input. Maps that into a tuple traces for the output. Okay, and just as before, we can model reactors with no inputs or no outputs by using the singleton set. This is going to be a singleton set, and it doesn't matter actually what the element of the set is. We define the tag set of the tuple of signals to be the union of the tag sets of the inputs. That's useful because you could have a tag where this input is present and this one is absent, right? But we're going to want to consider, tags where there's at least one input present. And so we can do that by just forming the union of the tag sets of the inputs. I'll come back to the question of discreteness in a minute. Okay. So now, what is a metric space? Well, a metric space is an algebraic structure that consists of a set and a metric distance function, d. So d is the metric distance function. And in the basic definition of a metric space, d takes two arguments, two elements from the set x, and yields a non-negative real number, right? And it has to satisfy, that function has to satisfy three properties. It has to satisfy what's called identity of indiscernibles, which means that the distance is zero only if the two arguments are the same. Makes sense, right? Distance between two objects should be zero only if they're the same object. You should have symmetry. The distance from x to y should be the same as the distance from y to x. And then you should have the triangle inequality, which is simply that the distance from between x and z is less than or equal to the distance between x and y and z. Okay, the sum of those two distances. So if you add these two distances, that's always got to be bigger than this distance. That's the triangle inequality. All right, and together these three properties always actually by themselves imply that the distance function is always non-negative. Right, so that's just a basic definition of a metric space. Now, we can define a narrower space, which is called an ultrametric, that simply replaces the triangle inequality so that instead of a sum here, we use a maximum. Okay. Now notice that that does not work for ordinary Euclidean geometry. Right? The distance between x and z here is not guaranteed to be less than or equal to the maximum of these two distances. Right? It is guaranteed to be less than or equal to the sum of those two distances, but not guaranteed to be less than or equal to the maximum of those two distances. So an ultrametric space is not that useful for ordinary Euclidean geometry, but it's going to turn out to be extremely useful for the geometry that we're about to construct. Okay. If you have a distance metric that satisfies this property, it will also obviously satisfy the triangle inequality, right? Because the maximum will always be less than or equal to the sum of two non-negative numbers. Right? Okay. Now, here's the mind-blowing part. Cantor metric. Suppose that I have two signals, S1 and S2. These are functions of tags, okay? Let's assume the tags are, think of them as time, right? And suppose S1 has a value at time 0, has a value at time 1, has a value at time 2, and then maybe has a different value at time 3. And suppose that S2 has a value, the same value, so let's call this V0, has the same value at 0 same value at 1, but a different value at 2. This is V2, this is V2 prime. All right. The Cantor metric is a distance between these two signals that is defined to be 1 over 2 to the tau, where tau is the earliest time at which these signals differ. So the distance between S1 and S2 for this particular case is 1/4. Okay, that seems a little weird. Why do we call that a distance? Well, let's look at the extreme cases. Suppose that S1 is identical to S2. Okay. Suppose that that's the whole thing. That's all we got. Those two signals are identical. What's the earliest time at which they differ? Well, we define that to be infinity. Okay. So now the distance between them, the tau, is infinity. And 1 over 2 to the infinity is 0. So the distance between two identical signals is 0. That's reassuring, right? That's the identity of indiscernibles. Notice now a signal that differs at an earlier time, right? Suppose that now we take a signal that differs at, the eraser's not working. The signal S2 has an extra value at 4 that S1 doesn't have. Okay, now tau is 4. That's the earliest time at which these two signals differ, which means that the distance between them is 1 over 2 to the 4th, which is 1/16, right? Which is significantly less than 1/4, which is what we got before when they differed at time 3. No, at time 2, sorry. So when two signals are more similar for longer, the distance between them decreases. Right? The earlier they differ, the bigger the distance between them. Okay? So that's called a Cantor metric. It was first used by Georg Cantor, same guy who figured out that there's more than one infinity. Okay, and anyway, it's also called the Baire distance because, like most things, it got reinvented independently by somebody else. But it's a pretty interesting distance function, and it turns out that you can easily prove that it's an ultrametric distance. Okay, it satisfies three properties, the stronger property than the triangle inequality. It satisfies the triangle inequality with the variant that's a maximization. Okay. So how does this help? Well, let's look at a few examples first. So suppose I have a signal, two possible signals, and I can sketch these, right? So S1 is a signal that has value 0 at time 1, and S2 has value 0 at time 1 and 0 at time 2. So what's the distance between those? One over 2 to the tau, where tau is the earliest time at which they differ. So it's 1/4, right? The earliest time at which they differ is 2. Okay. Now, a little more interesting. Suppose I have an infinite signal. Okay, this is one that has an infinite number of events. So corresponding to a lingua franca program that doesn't terminate. Okay, this is one of the nice things about this formalism is it doesn't require the programs to terminate. And we'll get a nice semantics for it. So Z is the set of all integers. So this signal S1 has value 0 at all the integers, all the way out unbounded, right? 0, 1, 2, etc. And then G2 is similar, except that, S2 is similar, except that instead of value 0, it has value 1 at all of these. Okay, 0, 1, 2. So now what is the distance between S1 and S2? It's 1. So one of the interesting things about this Cantor metric is that for the particular formalism that we've defined where we're looking at positive real numbers only for times, the distance is always between 0 and 1. Right? The distance between two signals will be 1 if they differ immediately at the start, and 0 if they never differ. And it's always going to be somewhere in between when they differ somewhere along the timeline. Okay? So there's the formalism. Yeah, so the answers are 1/4 and, whoa, oh, sorry. This has a different answer because Z is usually defined to be a set of all integers, positive and negative, right? As opposed to the natural numbers. I was thinking, I had the Z turned on its side. It becomes the natural numbers, right? So this would be a distance of 1 if the domain of this was the natural numbers, but I guess on this slide it was augmented so that this has value also at negative numbers for times. So now what's the earliest time at which these signals differ? Well, now it's going to be -infinity. They've always differed, okay? So tau is -infinity. 1/2 to the tau is infinity. So if you have two signals that have always differed since before time, the distance between them is infinite. So one of my PhD students pointed out that this metric gives you a nice formalism for what cosmologists speculate about, a multiplicity of universes that are separated from each other and can never interact, right? These are simply universes where this Cantor metric gives them an infinite distance between them, that they have differed since forever, before time. So that's a slightly bizarre interpretation, but fortunately in the context of lingua franca, we don't have to worry about that because every lingua franca program has a starting time, right? It may not have an ending time, but it always has a starting time. And consequently, we can always restrict ourselves to distances between 0 and 1. Okay. So, okay, there's some subtleties with this because it turns out that it's not always true that there is a time at which, a first time at which two signals differ. Okay, but let me skip those subtleties because that's not a problem with lingua franca. It becomes a problem when when time is actually a continuum, okay, and it isn't in lingua franca. So there's always going to be an earliest time at which the signals differ, if they differ at all. Yeah. So this is just this result that I already established, which is that if we restrict ourselves to the non-negative times, then we always end up with a distance between 0 and 1. This is simply a demonstration or an assertion. No, I guess it's a demonstration that this is an ultrametric. Okay. And there's a proof of the ultrametric inequality property here. I'll just ask you to take my word for it. You don't need to worry about it. And this just says that in a program like lingua franca, we don't have some of the usual subtleties that arise in metric spaces because we don't have a continuum for time. And so we don't have to worry about that. Okay. Now, once we have this metric, we can talk about causation. Okay. So in particular, a reactor F is causal if it satisfies this monotonicity property. Wait, why is that? Well, let's think about it. Suppose I have a reactor and I give it signal S1 and it produces F of S1. And I give it signal S2 and it produces F of S2, right? Suppose that the earliest time at which these two differ is tau, right? So the distance between them is 1/2 to the tau. What do you think the earliest time at which these two should differ is? Probably shouldn't be less than tau, right? If it's less than tau, we have an acausal system. We have a system that is able to anticipate future inputs. Okay? So the distance between these guys is always going to be less than or equal to the distance between the inputs. That's a monotonic function. Guess what? We can use theorems like the Kleene fixed point theorem because we have a monotonic function. All right? So the idea that you can use this formalism to represent causality, to me, is really quite beautiful. But it turns out we're going to need a couple of different forms of causality. We have a strict causality, which is where the distance between the outputs is strictly less than, rather than just less than or equals. Why do you think we're going to need that? Well, the answer is that it makes it much easier to deal with feedback loops. Okay, because think about it. The feedback loop is kind of going to be a bit of a challenge, right? Because when you have a feedback loop, the function is to find an infinite trace of an input, and it produces an infinite trace of an output. And you can't know what the infinite trace of the input is until you know what the infinite trace of the output is, which means you've got a fixed point problem. And it turns out that it's going to be exactly this property of causality that is going to ensure the existence of a fixed point and its uniqueness. Okay. So, yeah, so the intuition of causation is that, there's a third version of causation, which is delta causal, which means that there exists a real number delta that's less than 1, such that the distance between the outputs is less than or equal to delta times the distance between the inputs. And what this means from a practical perspective is that you have a lingua franca reactor where there's a delay, a logical delay on the output. So the output is dependent on inputs only at earlier, strictly earlier times. Okay, and never at exactly the same time. Okay, so now there's this whole mathematics around metric spaces that relates to what are called contracting functions. Okay. So if you've got a metric space and you've got a function is said to be contracting if the distance between the results of the function application is less than or equal to the distance between the inputs. Okay, it's said to be strictly contracting if it's a strict inequality, and delta contracting if it's if there's a delta. Okay, I contract. Think of a three-dimensional geometric space. Suppose that I've got 2 points and they've got some distance between them. And I apply a function to them that brings them closer together. Reduces the distance. Okay? If I apply the function again, reduces the distance further. If it's strictly contracting or delta contracting, it always reduces the distance. Okay? If it's delta contracting, you keep applying this function and eventually these 2 points will come together. Okay? That's your fixed point. As soon as the 2 points have come together, you now have 2 signals that are identical for all time. Okay, so the contracting terminology comes from this intuition in three-dimensional space where you can bring these functions together, and the fixed point arises when they merge into a single point. Okay. So you can generalize this to multiple inputs and outputs, no problem. You just have to work on tuples of signals, but I think I will spare you the details of that. You can handle reactors with no inputs or no outputs. And now we can use a fixed point theorem, which is a classic result in metric spaces, where if you have a function that is strictly contracting, then this theorem says that there is at most one fixed point. Okay, so that's going to be enough to give us uniqueness, but it doesn't give us by itself existence. I'm going to skip over some of these technicalities here. Well, maybe actually skip over this. So, by the way, what I'm doing here is these slides come from a course that I've taught several times at Berkeley, and it usually takes like a few weeks to build this up. And so you're getting a bit of a whirlwind tour. And so I'm trying to pick out the real nuggets that will give you some intuition about what's going on, right? So the key intuition here is that what we're dealing with now is functions that operate on infinite signals, produce infinite signals. That's the first piece of intuition, right? Which is quite different from what we did before with the semantics, where we were looking at an individual tag and the function was only operating on the current value of the inputs and producing the current value of the outputs. Now we're dealing with functions that look at the whole history of the input and give you the whole history of the output. And the second thing we're doing is constructing an algebraic space for those inputs and outputs, and then making these functions have this property of causality, which is an intuitive property, it's a desirable property, and then showing that that property translates into this very nice mathematical property of contraction, which then enables us to use these fixed point theorems to prove that any network of such reactors will always have a behavior and have exactly one behavior. Okay, so that's the the story, right? But the details can get pretty gnarly. And the key theorem that this depends on is this Banach fixed point theorem, okay, which says that if you have a set X and a metric on it, and there's a technicality that your metric space needs to be complete, which turns out to be an important technicality in our case, and we have to show that it's complete. Okay. I'm not going to do that. Then if you have a function that is delta contracting, then it turns out that the function has a unique fixed point, and interestingly enough, you can find that fixed point in a constructive way by starting with any arbitrary guess about what the signal is, and then applying the function over and over again. That's weird. So let me show you how this works with a concrete example. Suppose that I have a reactor that, given an input, it has a reaction and it schedules a logical action, which then schedules another reaction and produces an output. Okay, and suppose that the behavior of this particular reactor is that for any input event, say with tag value pair, it produces an output that is just delayed by 1. Okay. Hopefully you got enough intuition with lingua franca that you know how to write such a thing. You just need to call the schedule function to schedule a logical action 1 time unit later, and then that'll trigger this reaction, which will produce the output. Okay. So this is, in fact, a delta contracting function. Okay, given any input, suppose that I give it as an input S1 is, value 1 at 0, value 1 at 2, and nothing else. Okay, then S2 is going to have value 1 at 1, value 1 at 3, and then nothing else. Right? That's input, output. Wait a minute. That's not what I want to do to show that it's delta contracting. This is f of S1. Right? So to show that this function is contracting, I have to compare 2 possible inputs. So if I give it an input, say, let's call it S2, that is the same as S1, but has an additional value at 4, okay? Then what's the earliest time at which the inputs differ? Well, 4, right? So the distance between S1 and S2 is 1 over 2 to the 4th. What's the distance between f of S1 and f of S2? Well, let's figure out f of S2 is just a delayed version of S2. So that's going to be a 1 at time 1, a 1 at time 3, and a 1 at time 5. Right? So the distance between these 2 guys is 1 over 2 to the 5th, which is strictly less than this guy, 1 over 2 to the 4th. So we certainly have a strictly contracting function. You can also show that this is delta contracting. Okay. So let me now show you how the Banach fixed point theorem works for this. So suppose that I take this function, whoops, and I put it in a feedback loop like that. What do you think the behavior should be? You do have enough experience with lingua franca programs to be able to answer that question. Okay. What's going to happen if you write this program and compile it and run it? Do it. Fire up Banach and write the program. Convince you. First of all, will it yield a causality? No, there's no causality because of this logical action, right? Okay. So what do you think will happen when you execute this program? Yeah, nothing. There won't be any events. The program will start and exit, and will tell you that this signal is empty. It has no events. Okay. Let's see if the Banach fixed point theorem agrees. Okay. The Banach fixed point theorem says, oh, I can start with any guess at all about what this signal is. So let's start with a wild guess, right? I'll guess that the signal, that the behavior of this program is that it produces an event at time 5. Okay, and that's all it does. Wild guess. Okay, we know that's not what it does, but then what's the Banach, how is the Banach fixed point theorem going to prove this to us? Okay, well, the Banach fixed point theorem says, I just start with a wild guess and I apply the function to that wild guess. Okay, so I call this S, and I'll define this to be S0, and then S1 is the function applied to S0. So that's this signal delayed by 1. Right? If the input is an event at time 5, the output is going to be an event at time 6. No problem. Okay? I do it again. S2 now gets applied to the previous signal. The input is an event at time 6, so the output will be an event at time 7. I keep doing this. What happens? Well, the events keep moving out into the future. Okay? And the correct answer for this, the actual behavior that we're after, is the empty signal, which we label as lambda. So what happens to the distance between the correct signal and these S of K's? Well, the earliest time at which S of 0 differs from the correct answer is 5. Oops. Oh. Right? So there's a distance of 1 over 2 to the 5th initially, then 1 over 2 to the 6th, then 1 over 2 to the 7th. And these signals keep getting pushed out, further out, further out. The distance keeps decreasing between the correct answer and the incorrect answer. In the limit, the incorrect signal gets pushed out to infinity, okay? And the distance converges to 0. And so if you look at the limit of this sequence, the limit is actually the correct answer, the empty signal. That's crazy, right? This says, I mean, the Banach fixed point theorem is kind of telling us that if you have delta contracting functions, which are functions that are a little more than strictly causal, there's actually a non-zero time delay across them, okay? You can take any guess about the behavior of the feedback system, and the Banach fixed point theorem will tell you what the right behavior is eventually, right, in the limit, as a limit of a sequence. And the theorem tells you that the limit of that sequence is in fact unique, it exists, and it is a fixed point for this function. Okay, so this is a completely different way to construct the semantics from the one that we did before. It's one that operates on entire histories of signals instead of on individual values. There are technicalities that have to do with the completeness of the space. In particular, you have to be able to prove that the limit always exists, okay, and that it's in your space of signals. So these are technicalities you have to construct. In order to show that the limit exists, you have to construct this notion of Cauchy sequences, and then you get, a theorem where it tells you that every Cauchy sequence converges, and consequently you can apply the Banach fixed point theorem, and you're all done. Okay. So that's a very quick summary of something that, to give you the full development, really requires doing homework problems, working out the math for several examples, understanding the corner cases, carrying out the proofs, etc. To get that full story, you probably would need to come to Berkeley and take my class. Okay. So hopefully that was a useful glimpse into the world of the semantics of these concurrent programs. As a general picture, right, this style of computer science, where you look at the semantics of programs this way, using algebras, using fixed point theorems, and so on. There's a whole community that does this, and it's mostly a European-based community. In fact, there's this famous 2-volume set, which is a encyclopedia of computer science, okay, that has 2 volumes, volume A and volume B. And it's all about computer science theory. And all of this kind of semantics is in volume B, okay? And it's almost all European authors. And volume A is much more American authors, and it's more about complexity and algorithms. Okay, so the American style of theoretical computer science is very focused on complexity theory, and the European style is very focused on semantics. That's not perfect, of course. There are people on both sides of the Atlantic who do both kinds of work, but there is a stylistic difference there, and there's a strong preference that people have. And one of the things, I think I might have mentioned that the synchronous languages tend to be a largely French phenomenon. There's a lot of French researchers who work on synchronous languages, and that's partly because they find this mathematical formulation extremely beautiful. It is, actually. It's really quite nice to work with, and you can dive in sort of infinitely deeply into this. I mentioned that it can be kind of seductive. I've seen people, when graduate students take my class at Berkeley, sometimes they get so enthralled with this that they make it the rest of their career. And I do not recommend that, especially if you're a US researcher, where there isn't a lot of interest among US theoretical computer scientists in this kind of stuff. It's a much more European thing. So be careful. Avoid diving into it too deeply, because it might not do very good things for your career. But it is kind of fun if you like math. Okay, so let's stop there.